Hi everyone, welcome to this video on Cantor's diagonal proof. So, you've seen this definition before. A set X is countable if either X is finite or if X is in bijection with the set of natural numbers. We say that X is uncountable, naturally, if it is not countable. The theorem we're trying to show today is that the set of real numbers is an uncountable set. The method we're going to use to prove this claim is proof by contradiction. We suppose towards a contradiction that the set of real numbers is countable. We've got an infinite subset 0, 1 of the set of real numbers. And this isn't infinite by width, it's infinite by the number of elements it contains. Because it's an infinite subset of a countable set, we must have that it is countable itself. We can therefore create a bijection f from the set of natural numbers to this interval 0, 1. Now we're going to use the fact that every real number has a decimal expansion. We're going to write the action of f as follows. F of 1 is equal to 0.A11, A12, A13, etc., going up to A1n and beyond. So this is just a decimal expansion as you've seen before. So this could be 0.125, something like that is equal to f of 1. We do the same for f of 2, f of 3, and so on, going up to f of n. So these are just these numbers, but expressed in decimal. We next use the fact that f is a bijection. And bijections are just functions which are both injective and surjective. So f is a surjection as well. What this means is that every single element of this range 0, 1 must be equal to f of j for some natural number j. This is just the definition of surjective functions. Now we come to our claim that will provide us our contradiction. So we claim that we can find some element b which belongs to the range 0, 1 such that f of m is not equal to b for every natural number m. So if we look at our list, we're saying that we can find some natural number b for which b is not contained on this list. This will give us our desired contradiction because we assume that the function f was bijective and hence surjective. If there is an element b in the range 0, 1 which does not belong to the list, then f cannot be a bijection. To this end, for every single natural number m, we're going to choose some bm that belongs to the set 1 going up to 8, for which bm is not equal to amm. Now this is probably easiest to see once we reveal the number b and we reveal all of the elements in the list. So what have we done when we've created this number b? b1 is not equal to a11, b2 is not equal to a22, b3 is not equal to a33, and so on. Every single sort of diagonal element in this list is the point in which it's not equal to b. So for every natural number m, b is different to f of m in the mth decimal place. b cannot be equal to f of m for every single natural number m, which is the kind of thing we were trying to prove to get our contradiction. You can kind of see why this is called diagonal proof because of the fact that it's different in all of these diagonal positions, in these diagonal decimal places from the elements of the list. Now, some of you might be wondering why the decimal places bm of b are not allowed to be 0 or 9. Why would I only make this range from 1 to 8? Well, the fact is that decimal expansions actually are not unique. There can be one number which has two decimal expansions. For example, 0.19999 recurring is equal to 0.2. So if I'd have allowed zeros and nines on this, perhaps one of these numbers, f of m, has the decimal expansion 0.199999. And if I'd allowed bm to contain the digit 0 as well, b could be equal to 0.2000, etc. And this would mean that b is equal to f of m, so it does belong on the list. So to avoid that kind of situation and ensure that b doesn't belong to the list, we've removed the digits for which, if b had contained them, it might have been a non-unique decimal expansion. So now we've completed our goal of showing that the set of natural numbers is not in bijection with the set of real numbers. We've proved though there are different kinds of infinity. There is a countable infinity and there's an uncountable infinity. And I just wanted to spend a couple of minutes with this further discussion section talking about some of the implications of this. Well, if we write x in these kind of straight lines for the cardinality of the set x, what Cantor's power set theorem tells us is that if we take the natural numbers, an infinite set, the cardinality of its power set is strictly greater than its cardinality. The cardinality of the power set of that set is even bigger. The cardinality of the power set of that set is even bigger, and so on. You can have infinitely many infinite cardinalities. So this weird situation where you have an infinite set with a greater cardinality than another infinite set, it actually continues in this kind of ordered fashion forever. We know that the natural numbers are a subset of the real numbers. This is obvious. We know that these two sets are not in bijection. This is what we proved today with our diagonal proof. So we have that the set of natural numbers has a lesser cardinality than the set of real numbers. What we might wonder is the following. If we take a subset of the reals, is it necessarily true that x is a finite or countably infinite set? So is x countable, or is x equal in cardinality to the reals? Does x have a bijection between it and the reals? So this question here, is x either countable or in bijection with the reals whenever x is a subset of the reals? This is the continuum hypothesis. Now, this is famously very, very tricky question because within the standard axioms, these are kind of the set of logical building blocks on which set theory is created. This question cannot be proved or disproved. You can prove that it can't be proved or disproved, but you cannot find a proof or disproof of this claim, which is quite astonishing. This is a very complicated and deep set theoretic proof that was completed by Paul Cohen sometime in the 1960s. Now, this is way beyond the scope of this course, but there's further discussion just to talk about the implications of the diagonal proof, of the fact that you have these different infinite cardinalities, and Cantor's power set theorem. I would advise you, after watching this video, go and see the proof of Cantor's power set theorem, because it uses some similar elements to this diagonal proof, but it's also it relies on a very fun trick in and of itself, and it definitely will be accessible to you if you've made it this far in the course already. Thank you for listening. I'll see you next time.